So section 3.6 is going to discuss rational functions. Rational functions have this form. R of x is P of x over Q of x. Now, P of x and Q of x are understood to be polynomials. So the kind of stuff that we've been studying the entire rest of this chapter, P of x and Q of x are polynomials. And we want to look at the graphs of these rational functions. Now we're going to start by trying to get familiar with the most basic rational function, and that is y equals 1 over x. So what's that going to look like? And we're going to do a little bit of experimenting. So we've got our function already entered into our graphing calculator here. Y equals 1 over x. Let's actually make a little bit of a table for this. So I'll hit the second key, then the graph key. That takes me to the table. And I'm going to plug in values for x. Now, when I do this, there's one value of x that's going to create a little bit of a problem. Can you see what value of x is going to create a problem? 0. So let's kind of do like what my son does. When I tell him, well, you have to eat in the kitchen, and he comes closer and closer and closer to the edge of that kitchen door. He's like really, really close. So let's see what happens if we get really, really close to 0. So we'll start out with like a 0.5. If I put in 0.5, well, reciprocal of 1/2 is 2. That makes sense. We'll put in 0.1. Now I get 10. 0.01. 100. 0.001. Any predictions? 1,000. And you can see that as you keep on putting in more and more zeros, getting closer and closer to 0, what's happening to the y value? It's getting really, really big, right? So when you divide something fixed, like the number 1, by something that's getting really, really small, you're going to get a bigger and bigger quotient, a bigger and bigger number. Now, you don't have to approach 0 from just the positive side. You can approach 0 from the negative side as well. So let's do the same thing, except plug in negative 0.5, negative 0.1, negative 0.01, and negative 0.001. Are we getting more or less the same kind of behavior? Yeah, except there's one difference. What's our one difference? Yeah, instead of numbers going up and up and up and up in the positive direction, this time they're going down and down and down in the negative direction. So, okay, what's the graph of this look like then? Well, let's check it out here. So, for our window, let's set up our window, say, from negative, let's do negative 4 to 4 on the x-axis, and negative 3 to 3 on the y-axis. And then hit the graph key and see what we get. And you get two kind of branches of this graph. And to the right of the y-axis, that is for positive values of x, you can see what we saw on the table. That is, this branch of the graph approaches positive infinity. But if we skip over a little bit to the left, now this graph approaches negative infinity. And this line itself here, x equals 0, has a special name. Does anyone know what those kind of lines are called? Asymptotes. This is a vertical asymptote. This graph approaches but never quite touches its vertical asymptote. Now, before we started rolling on this video, I asked you to also plug in y equals 1 over x squared. Let's go back and highlight that graph. So press the enter key on that equals. And now let's take a look at the table and see if I get any different type of behavior from this graph as opposed to 1 over x. So if I hit the second key, then the table key, and now I get a bunch of different numbers. For instance, I get a 2 and a 100 and a 10,000. So one thing that's going on is that these numbers are getting bigger faster. So this is going to approach positive infinity even quicker. In fact, what does 1e6 represent? Does anyone know? Yeah, it's in scientific notation. It means 1 times 10 to the 6, or basically 1 million. And this would be 100 million. and so on. But the other important difference here is what? It's that this graph is always positive, right? And that's because when you square this, you've got a positive number. And a positive divided by a positive is still going to be positive. So great. That's your graph of 1 over x. And like I said, there's something interesting to notice about that, and that you've got a vertical asymptote. But let me look at the graph of y equals 1 over x squared. I still have a vertical asymptote. This time my graph is in red. But in addition to my vertical asymptote, there's also something else going on with both of these graphs. As I move away from x equals 0 in either direction, what happens to the graphs? Well, it doesn't quite touch the line, but it gets closer and closer to the line y equals 0. So it has, in addition to a vertical asymptote, it has a horizontal asymptote. It's got both of them. So there's a lot going on with these graphs. And our job in this section is to find the vertical asymptote, the horizontal asymptote, the X and Y-intercepts, and then, of course, graph it. Now, on an exam, I'm not going to take away your graphing calculator. You can do that. But I still need you to be able to find these things without necessarily relying on your graphing calculator, because there's only so much that a graphing calculator can tell you. Are you okay with the graph of this and maybe understand a little bit about why it behaves the way it does? So let's compare this now to problem number 16. Y equals 1 over x plus 4. These two graphs should be similar. In fact, this one has just been shifted from this one. But how has it been shifted? Can anyone figure this out? Actually, this is problem number 14, my bad. Yeah, this one's been shifted to the left by 4. And the thing is, you can see and predict where the new vertical asymptote is going to be. The vertical asymptote in this one was at x equals 0. Where's the vertical asymptote in this one going to be? Should be at x equals negative 4. Let's actually glimpse that by looking at the graph here. So here's your graph of 1 over x. And there's your graph of 1 over x plus 4. Let's get rid of that one. And you can see that you've got a vertical asymptote here, right there. Now, your graphing calculator is not going to put this line in for you, generally speaking, but it's just kind of a feature of the graph that you want to be aware of, that the graph gets closer and closer to that point without touching it. How are we looking at problem number 14 there? All right. I said it was problem 16, but I was wrong. Here's problem 16. Y equals negative 2 over x minus 2. Now, again, you're going to get some shifting from this original graph. And there's three things that are going to happen in looking at the graph of this compared to the graph of this. Let's see if we can't spot them. Ashley, what's one of the shifts that you see? 2 which way? Good. Shifted right by 2. Good. What else do we see? Andrew? Nice. So the negative flips the graph around the x-axis. So it's been flipped. And the 2 here means it's been stretched. So it's stretched away from the x-axis. Stretched away from the x-axis. Nice. Grab yourself a handout over there. Oh, okay. That's good. Yeah, same thing. Cool. Let's actually see the graph and see that it has all these features. So here's your original graph, 1 over x, and here's the other one. So you can see that it's been flipped. Instead of near its vertical asymptote going up from the right side, it goes up from the left side. It's been stretched away, and our new vertical asymptote has also been shifted. So we have a vertical asymptote at x equals 2 as opposed to x equals 0. So perfect. Got all the features that I was looking for there. Now, let's add some stuff to this. For instance, I might want to know in general where this graph crosses the axes. This one in particular has a Y-intercept at 1. But I want to be able to find the Y-intercepts and the X-intercepts in general without necessarily always having to look back at the graph. And the graphs can be kind of challenging sometimes, so let's work on that. So finding the X and Y-intercepts. X and Y-intercepts. Okay. Well, for the Y-intercept, well, what do we do to find the Y-intercept of anything? Yeah, set x equals 0. That should be pretty easy for us. Set x equals 0. For our X-intercepts, yeah, you're going to set y equal to 0. Now keep in mind that we're going to set y equal to 0 in a situation like this. R of x equals p of x over q of x. Now, in something like this, my r of x is really the y. So effectively, I'm going to set y equals 0. Now, if you want to just kind of sit back and relax for a second and take notes, that's fine. Or maybe you just want to wait until the happy ending, which is coming up pretty quickly. So just relax and take out the happy ending. I want to solve for where this is equal to 0. But I look at that and I'm like, you know what? I know you guys, you don't like fractions. You just hate working with fractions. So if I had a problem that was working with fractions, I always tell my students, get rid of the fractions. I'll multiply both sides by q of x. Now on the right-hand side, I get the q of x cancels itself out. What about on the left-hand side? What happens on the left-hand side? What's 0 times anything? 0. So I get 0 equals p of x. In other words, if I want to find the roots of this, the X-intercepts, then I want to find out where the numerator is equal to 0. I don't have to worry about the denominator at all. So that's something to keep in mind moving forward on this. Okay, so let's do that with problem number 22. In fact, what I just highlighted is on your handout. So we found the Y-intercept by setting x equal to 0. That's not too healthy. So your Y-intercept, set x equals 0. For the X-intercept, set p of x equal to 0. So we got that one. X-intercepts, p of x equals 0. And we're going to try and find some asymptotes coming up, but we'll get back to that in just a second. Let's work with problem number 22. So problem 22 gives us s of x. S of x is 3x over x minus 5. And I want two things here. I want the X-intercepts, and I want the Y-intercept. So, okay. This one's kind of almost a little bit too simple for us in the following sense. And we'll see. I'll start out by setting x equal to 0. If I set x equals 0, that'd be my Y-intercept. It'd be s of 0 equals 3 times 0 over 0 minus 5. What's 0 divided by negative 5? 0. So if I set x equals 0, I get y equals 0. Okay. Well, what else? If I want to find the x-intercept, then I'm going to set the numerator equal to 0. And not thinking about this too carefully, I just kind of boldly charge ahead and say, all right, well, the numerator equals 0, 3x equals 0. When is that true? What value of x makes this equal to 0? Wow, I didn't get what I expected. How would you solve here? Divide by 3, right? So divide by 3, and we get 0. Remember, you're supposed to make me look good. This is live, right? We're live casting. No. All right, we're not really live casting, but anyways, make me look good. And in hindsight, I was like, oh, duh, I get x equals 0. Well, I could have predicted it, right? You set y equals 0, you're going to get x equals 0. Now, sometimes you might get an extra one, so it's not a big deal that we checked it, but your x and y-intercept are really the same point because this graph passes through the origin. Let's try a slightly different one. Problem number 24. This time we've got r of x is 2 over x squared plus 3x minus 4. So there's a couple things that we want here. We want the x-intercepts and the y-intercept. So as before, we'll start out by setting x equal to 0. So r of 0 can anyone just read off what r of 0 is going to be? Over negative 4, which is negative 1/2. So the graph of this should cross the y-axis at 0 and negative 1/2. So that's my y-intercept. What do I have to do to find the x-intercept? Set the numerator equal to 0. Notice it's just the numerator. It's not the whole thing equal to 0. Let's make our life easier. It's just the numerator equal to 0. So you're going to have to help me out on this one because it's confusing. X-intercept. Well, what's the numerator? And I need to set that equal to 0. Does 2 equal 0? No. Not last time I checked. So what that says is that there's no x-intercept. And that the graph is not crossing the x-axis at all. It might come close to it, but it won't actually cross that. So that's what it's telling us there. Let's actually look at that graph and pick out a few more things about it. So that's this equation here. And you can see that the graph doesn't quite touch the x-axis. It comes close to it, but it doesn't touch it. And if I click here, it should tell me my y-intercept, 0, negative 0.5. So it matches all our expectations. Well, let's raise our expectations a little bit. What kind of features do you notice, say, here at 1 and here at negative 4? Thank you. Vertical asymptotes. So how do you predict where there's going to be a vertical asymptote? Well, what if I factored the denominator? What if instead of writing this, I wrote it factored? what problems can I run into with different values of x? At -4 and at 1, the denominator is 0. You can't divide by 0. And we're seeing that same kind of problem here that we saw with the graph of 1 over x. You're getting a vertical asymptote when you divide by 0. And that's a problem. It's a problem for this graph. That's why you're getting these spikes here. So not only does this graph have 2 vertical asymptotes, but it also has something else going on. It has a horizontal asymptote of y equals 0. So, wow, okay. There's a lot going on. Let's understand it. Let's go back to our handout. So going back to our handout, we're going to come down to this part right here. Find and graph any horizontal/oblique asymptotes. We're just going to work with the horizontal asymptotes for the moment. The oblique asymptotes is going to come in just a minute. Well, maybe a little bit more than a minute. But so there's a couple cases. There's case A, where the degree of the numerator is less than the degree of the denominator. So that's the first case. And if that's true, then y equals 0 is your horizontal asymptote. Now let's just look back at our previous example, problem 24. What's the degree of the denominator term? What's the degree of that polynomial? 2. And the degree of the numerator is 0, because it's a polynomial. If it was a linear term like 3x minus 4, then the degree would be 1. If it's just a constant term, then it's a degree 0. So you have a degree 0 here and a degree 2 here. So the degree of the denominator is bigger than the degree of the numerator. In fact, it exactly fits this case. And we saw that y equals 0 was a horizontal asymptote. What else can happen? Well, you can have case B. If the degrees equal each other, that is, the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is going to change. It's just going to be y equals some number, and that number is going to be the ratio of the leading coefficients. Let's practice a couple, first visually and then a little bit more formally. So let's practice them visually by looking at problem number 28. One thing you have to notice on problem number 28 is the scale. If I move over 2, then that puts me at x equal 1. You should be able to see that this graph has a couple vertical asymptotes. Where are those vertical asymptotes? So remember, when you move 2 spaces, 1, 2, that's really x equal 1. If I move 2 more, where is that one? 2. So at x equal 2, and where else? X equal -2. So at those 2 points, I've got, -1. At -1 and at 2, I've got vertical asymptotes. Now, before I write that down, let me just ask you kind of a quick question. If I was to ask you to graph, say, I don't know, say 3, what would you do? Where would you graph that? Yeah, is it x or y? It makes a difference because x equals something is a vertical graph. That's a vertical line, x equal 2. And x equal -1. Those are your vertical asymptotes. So if you just give me 2 and -1, I get a little uncomfortable because I need to know, is that your vertical line or is that a horizontal line? So please, when I give you these questions, give me x equals something or y equals something. As far as the rest of this is concerned, There's a few more questions we got to answer. Is there a horizontal asymptote in this one? Yeah, it looks like y equals 0. It looks like the graph is getting close to y equals 0 either way. That's actually kind of cool. Should I leave it like that? Yes? Okay. That's okay. Actually, it does cross the x-axis right at the origin, but that gives us the answer to a different question. It asks you to define the x and y-intercepts. In this case, the x and y-intercepts are the same, be 0 and 0. So that's another part of this question, but it's not doesn't mean that you can't have a horizontal asymptote. You can cross your horizontal asymptotes. So y equals 0 is your horizontal asymptote, and 0, 0 are your x and y intercepts. Yep. But just because something crosses the horizontal asymptote doesn't mean that it's not a horizontal asymptote anymore. I know it feels like they should always stay on one side of the horizontal asymptote, but they don't necessarily. Once you move away from x equals 0, that is the y-axis, then it tends to stay on one side or the other. It generally doesn't bounce up and down, although you can have graphs that do bounce up and down. Let's do a follow-up with that one. Are we okay with our conclusions on this one? These are your vertical asymptotes, and that's your horizontal asymptote, and then that's your x and y intercepts. Try likewise with problem number 30. So again, see if you can't find the asymptotes and the intercepts. They may or may not be plural. It's just another graph. I'm trying to think what function I would use to create that. Yeah. It does look a little bit like a sinkhole. So maybe you'd find this graph in Florida, right? Okay, almond. What do you see in terms of? There's room up front. Right here. Someone else. What are we seeing? What do you see for the graph in terms of asymptotes? Well, -2 and 2 would be your x-intercepts, right? So here and here, that'd be your x-intercepts. So -2, 0, and 2, 0, those are your x-intercepts. Good. And let's get rid of the last intercept. What's the y-intercept? Yeah, 0, -6. So those are our intercepts. How about any asymptotes? Are there any asymptotes on this one? Which one? X equal 2 or y equals 2? Good. Y equals 2, because you got a horizontal asymptote right here at y equals 2. So that's the only one. You don't get a vertical asymptote here because the graph doesn't really kind of continue down towards negative infinity. It just kind of bounces back up. So there it is. That's all there is. There's only one asymptote, and that's y equals 2. Yes, ma'am. Yeah, so the graph, and they actually drew in a little dashed line here for you to kind of help out. But the graph is getting close to, but never quite touches that horizontal line. So that's why you've got a horizontal asymptote there. So to kind of summarize things, let me kind of zoom out a little bit. For problem number 30, we had y equals 2 was your horizontal asymptote, and then we had roots at -2, 0, 2, 0, and a y-intercept at 0, -6. Y-intercept. That's pretty much it for that graph. what I'm hoping is that you're getting accustomed to visually seeing what these features are. Your horizontal asymptote, your vertical asymptotes. We're next going to spend a little time playing and trying to find these things just by looking at the equations and making sure that our predictions, what we think is going to happen, actually does appear on our graph. Anything else on 28 or 30 before I move on to problem number 44? Okay, let's play around with problem 44 then. So R of x is 2x plus 6 over negative 6x plus 3. The first thing I want to do, the easy thing to do, a couple easy points, or maybe at least one easy point, is find the Y-intercept. How do we find the Y-intercept? Set x equal to 0. So R of 0 is going to be 2 times 0 plus 6 over negative 6 times 0 plus 3. And let's see what happens. You should end up with 6 over 3, which is 2. Okay. Now let's keep track of this in the form of a little t-table. So 0 and 2. How about the X-Intercept? What do I have to do to find the X-Intercept? Excellent. Set the numerator equal to 0. So let's do that. That's going to be 2x plus 6 equals 0, which means 2x equals negative 6, or x equals negative 3. So setting this to 0 gave me negative 3 for x. So all right, I've got a couple points here. Let's keep going. Let's work on the vertical asymptote. Vertical asymptote. How do we find the vertical asymptotes? Let's see. Well, that one's down here. You find the vertical asymptotes by setting the denominator equal to 0. Vertical asymptotes by setting q of x equals 0 and solving. So, okay. And just FYI, when you set equal to 0 and solve, in terms of looking for asymptotes, we're not going to worry about imaginary roots here, just the real roots. So the denominator in this case is negative 6x plus 3. So let's carefully set negative 6x plus 3 equal to 0. I'm just going to double check my sound here because I bumped this. We got sound still? Yes. Good. And if you carefully solve this, let me move this 6x to the other side. 3 equals 6x. What does x equal? Good, it's 1/2. So I should get a vertical asymptote at 1/2 when I graph this. And when we finally get around to graphing this, we'll double check that we do. We're also going to look for a horizontal asymptote. Zoom out a little bit here. Now, I've only gone over a couple cases for horizontal asymptotes so far. It was case A and case B. And let me just get rid of this for a second. So for case A and case B, case A was the degree of the numerator is less than the degree of the denominator. Case B is that they're equal. which is it case A or case B for problem number 44 here? B. The degree of these match. They're both equal to 1. What that means is that the ratio of those leading coefficients is going to give us our horizontal asymptote. So it's going to be y equals 2 over negative 6, which reduces to negative 1/3. Wow. So there's a lot going on there that we need to verify. And we're going to do that by graphing it on our graphing calculator. But are we okay with the 4 different things that we have that we found here? Our X and Y-intercepts, our vertical and horizontal asymptotes. Looking good on those? Dwayne? Sure. So even though it's not really written, what's the degree of this polynomial understood to be? 1. And the degree of this polynomial is also 1. So when the degrees of these match, when they're equal, then to find the equation of your horizontal asymptote, you're going to look at the leading coefficients. So the leading coefficients are the coefficients in front of these terms. So the 2 and the negative 6. Your horizontal asymptote is going to be the ratio of those. 2 divided by negative 6, and I reduce that to negative 1/3. Well, if the degrees don't match, then it could be that the degree of the numerator is less than the degree of the denominator, in which case y equals 0 is your horizontal asymptote. And there's one more case that we'll get to in a little bit. Let's put these in our graphing calculator and see what we get. So there's a couple different ways you can put this into your graphing calculator. Let me just kind of do the brute force approach on this one. Left parentheses 2x plus 6, right parentheses, divided by left parentheses negative 6x plus 3. You have to put the parentheses. Now, if you're like, oh, I know I'm going to forget the parentheses, I know I'm going to make a mistake, then your alternative to that would be to hit the alpha key, alpha, then y equals, alpha, y equals, and the first option down there is to do a fraction in kind of a more regular way, the kind of way we'd write it. And here you can put 2x plus 6, and then go down to the denominator and put minus 6x plus 3. So either way will give you the same graph. It's just that this way you got to be a little bit more careful that you have the parentheses. So it's up to you. Now I'm going to shut this one off because I don't need to graph twice. Let's set up our window. And this is the window that I have here from previous work, -4 to 4, -3 to 3. Let's just see what that gives us. We can always make an adjustment. That doesn't look too bad. Now, there's a few things that I might want to verify as I look at this. So, one of the things I might want to verify is the Y-intercept. If you hit the trace key, it starts out by putting a point right on my y-axis, 0 and 2. Well, that's what we got earlier. What other point did we expect to see on our graph? -3 and 0. So I've already hit the trace key. If I type in -3 and press enter, it tells me, all right, at x equals -3, you get y equals 0. Again, that's what we expected. What else did I expect in this graph? What other features? Asymptote, all right? So what was the asymptote? X equals 1/2. Now, it's a real pain to try and get this graph, the graphing calculator to draw an x equals something. But I can do the horizontal asymptote. So let's add in, I'm just going to clear this one out, -1 divided by 3. So y equals that. My graph should get close to that line. That looks pretty good. If you wanted to see it get closer, we'd have to widen our view. So if I widen my view to say -7 to 7, that should be probably wide enough that I could start really seeing that the graph gets close to -1/3. And of course, you can go much, much bigger than that. But at least this gives us a good general idea that, yeah, I think we're right in our calculations that the graph is getting close to that horizontal line. So it's nice that you can verify everything that we saw here. Anything on problem 44 that hasn't been carefully explained yet? Something that you're not quite sure about? Well, you can kind of see. Well, that's what I said. It's hard to graph it vertically, to do a vertical line. Let me just double check here. Yeah, there is a way that you can make it graph a vertical line, but it's really not worth our effort. But we know where that vertical line should be, right? It should be at x equal 1/2. So between 0 and 1, around here, 1/2, does it look reasonable that we might have a vertical line or a vertical asymptote? Yeah, it looks reasonable. All right, it's not going to be a complete fail-safe double check, but it looks reasonable that there's a vertical line here at 1/2. Certainly, you should be able to tell the difference between that and maybe if I put in a negative here, if I were to graph this one, then my vertical asymptote would now be at -1/2. So, yeah, if I was expecting one at 1/2, then I might look at it and go, well, wait a minute, something looks wrong. Yeah, so good question. You can't exactly check it with your graphing calculator for your vertical asymptote, but you should be able to get pretty reasonably close. Let's try problem number 54. R of x is 2x squared plus 10x minus 12 over x squared plus x minus 6. So again, trying to put everything together. Let's start out with the easy stuff, and that is by finding the X and Y-intercepts. I'm hoping that somebody can just read off the Y-intercept. If you put in a 0, so R of 0, there's only going to be two terms that are left, right? -12 over -6, thank you, is 2. How about my X-intercepts? What are the X-intercepts going to be, or how do I find those? All right, so, Sean, what should I do to find the X-intercepts? Perfect. 2x squared plus 10x minus 12 equals 0. Just set the numerator equals 0. You don't have to worry about the denominator equals 0. Thank you. As far as solving this is concerned, I see something that might make my life a little bit easier. Does anyone else see it? Divide everything by 2. That leaves me with x squared plus 5x minus 6 equals 0. And the nice thing there is that that'll factor pretty effortlessly. plus 6 and minus 1. So my vertical asymptotes are at what values? Good. So my vertical asymptotes, actually, you know what? These are my X-intercepts. My bad. What am I thinking? I haven't done the vertical asymptotes yet. So my X-intercepts, that happens when y is 0. So I get negative 6 and positive 1. Let's go chasing after the vertical asymptotes next. So, vertical asymptote. How am I going to find the vertical asymptotes? Set the denominator equals 0. So it's going to be x squared plus x minus 6 equals 0. And again, some friendly factorization. Plus 3 and minus 2. There's your vertical asymptotes. Please make sure you give me the x equals negative 3 and the x equals 2. One last thing to take care of, and that's our horizontal asymptotes. Bless you. Actually, singular, not plural. It's only going to be one. So r of x is 2x squared plus 10x minus 12 over x squared plus x minus 6. George? It's a good question. Are we using case B for this problem? Well, how do the degrees in the numerator and denominator line up? Is it case A or case B or something else? Case B. Both of these have the same degree. Both of them are degree 2. So it's case A. Pardon me, B. Case B. Now, even though it's not written, what's understood to be in front of the x squared term? A 1. And it's the ratio of the leading coefficients that represents our horizontal asymptote. So it's y equals 2 over 1, or better yet, just 2. So y equals 2 is the equation of your horizontal asymptote. Wow. A lot of stuff going on in that one. Whew. Deep breath. We'll see if we can't verify some of that stuff. Now you can verify it on your graphing calculator. I'm not going to take the time to do it there. Let's do it here on Desmos. I sent you the link earlier. So we saw that we had a vertical asymptote at -3 and another one at 2. Horizontal asymptote at y equal 2. Now your graph can cross the horizontal asymptote. So especially in and around x equals 0, closer towards the y-axis, it can cross it. But once you get out away from that, either to the right or to the left, it should stay steady. Let's see that happens. And it does. So you can kind of see that once you move away from x equals 0, you're getting out towards infinity or negative infinity, that the graph settles down and gets closer to its horizontal asymptote. Let's see if it has some of the other features we expected. It has a y-intercept at 0, 2. An x-intercept here should be at 1. Where's the other one? -6. So it has all the features that we expected from this graph. Any comments or thoughts on problem number 54 here? Looking all right with that one? All right, there was one last case that we have to deal with in terms of asymptotes. Let's look at our handout first. So coming back here. And it's case C. If the degree of the numerator, what's that saying? Basically, it's saying the degree of the numerator is 1 more than the degree of the denominator. Then what happens is that your asymptote is y equal the quotient, where what you're going to do is you're going to divide the numerator by the denominator. You get a quotient and remainder. The quotient part right here is going to be your oblique asymptote, or the book likes to call it a slant asymptote. I'm not sure which one is more old school or not, but the book uses slant asymptote here, where I use oblique asymptote. They both mean the same thing, that your asymptote is on a little bit of an angle. So problem number 70. R of x is x squared plus 2x over x minus 1. Same kind of game. We'll start off by trying to find the X and Y-Intercepts, and then the vertical asymptote, and then whatever else from there. I'll make us a little t-table here. We'll start off by setting x equal to 0. That'll get us our Y-intercept. So if x equals 0, well, what happens if I put in an x equals 0? Thank you. 0 for x gives me 0 for y. Now let's find the X-intercepts. What do I have to do to find the X-intercepts? Thank you. Set the numerator equal to 0. So x squared plus 2x equals 0. Certainly we don't need to pull out the quadratic formula for this one. This one factors. X times x plus 2. And I get two solutions, right? X equals 0, which we already knew, and x equals negative 2. So negative 2 and 0. This point is kind of doing double duty here, right? It's an X-intercept and it's a Y-intercept. So even though we kind of solved and we got 3 different points, 2 of them are really the same, 0, 0. Where's your vertical asymptote? All right. So set the denominator equal to 0. X minus 1 equals 0. Someone want to solve that one for me? Thank you. X equal 1. So that's your vertical asymptote. All right. Finally, it's come down to the horizontal / oblique asymptotes. Which case is this one? A, B, or C? Got to vote for A. What's the degree of the numerator? And the degree of the denominator? So is the degree of the numerator less than the degree of the denominator? And they're not equal. It's case C. So what you have to do is you have to divide this and look at the quotient. Now, I don't really care about the remainder, but we've got to do the quotient. And there's 2 different possibilities. You can do it by log division, or you can do it by synthetic division. Any preference? Synthetic? All right. Yeah, I kind of Not surprised on that one. Yeah, long division is not that fun. So if we're going to do this synthetically to find our slant asymptote, then what number goes out in front? A 1. Good. And what numbers go underneath here? 1, 2. Ooh. You'd struggle if you just did 1 and 2. It's not really written, but it's understood that there's a 0 there. And we got to have that 0. Put a vertical line going down. Synthetic division starts out with a 0. Well done. You're making me look good. Thank you. 0. Add, multiply, add, multiply. Yeah. All right. So 1, 1, 3, 3, and 3. So x squared plus 2x x squared plus 2x over x minus 1 equals, well, what is this saying to me? What's that saying? X plus 3 plus 3 over x minus 1. That's great. But what did I need from all that? I need that part right there. That's my quotient. This is the remainder. So my quotient tells me that the oblique asymptote is y equals x plus 3. That's your oblique asymptote. Let's put all this stuff together and take a look at its graph. Is there any one part of this that you want me to go over a little bit more before we take a look at the graph? Yes? It's if p is greater than q by 1. So if I had a cubic up here and a first degree down here, then it wouldn't give me a nice oblique asymptote. It'd be something different. So yeah, it's only for the special case where this is greater than this degree by exactly 1. And you had a question here too. Oh, because we're dividing by x minus 1, and you change the sign. So that's why we got a positive 1. We went from negative 1 to positive 1. Thank you. Other ones, George? Yeah. That's from the synthetic division. So the way this starts out, this is your constant term. This is the coefficient of x. If I had anything more, it would be the coefficient of x squared, x cubed, etc. You move from right to left. So these are all your coefficients, and this last one here is your remainder. And you put the remainder over the divisor, which is your x minus 1. So that's where we got this part. George? This isn't horizontal though, right? It's going to be the line x equals or y equals x plus 3. So it's no longer a horizontal asymptote, and we'll see that when I cut over to the graph. So anything more before I do look at that graph? Let's take a look at that. So let's get rid of this one, these, hasta la vista. And I think my viewing window should be pretty good for this one. But I put suggestions in these things. When I sent out the link to you yesterday night, I had a suggestion for the windows here. Here's your graph. Here's your vertical asymptote. And here's your oblique asymptote. So, yeah, it kind of matches along with everything we expected. Now, it doesn't have a horizontal asymptote at all, does it? The asymptote that approaches is kind of on a slant, hence the name. But other than that, it looks pretty good. We've got your Y-intercept here, X-intercept here. vertical asymptote, slant asymptote. Looks pretty good. Anything to wrap this one up? Okay. Well, I'd like to give you some homework then. Really like to do some more, but we've got another section to cover today. So for homework, try 9 through 55, 65, 69 through 75, and 77 got circled as a bonus. Okay, have fun.